Good morning. I am Dr. Akila, Assistant Professor, Department of Chemistry, Sri Sarada College for Women. Students, today we are going to see about VSEPR Theory, The Effect of Lone Pairs. This is our today's topic. So, what is VSEPR Theory? It is nothing but of valence-shell electron pair repulsion theory. Okay, the electron pair which are present in the valence shell undergo repulsion. So, due to that, what happens? That is what the topic today. Okay, by using VSEPR theory, what we can predict or what we can identify? Yes, we can identify the shape of a molecule or geometry of a molecule. Okay, how we can identify or how we can predict the shape of a molecule means depend upon the number of electron pair which are present in the valence shell of a central metal atom only we can predict the shape of a molecule. Okay. So what is valence shell? So consider this is an atom. An atom consists of several cells like K, L, M, N. Okay, the outermost cell is nothing but of valence shell. Okay, the electron which are present in the valence shell is said to be the valence shell electrons. Okay, so then electron pair. Electron pair has been classified into two types. Okay, one is lone pair, another one is bond pair. Lone pair means the electrons which are not involved in bonding. Okay, that electrons are said to be the lone pair of electron. In bond pair, the electrons which are involved in bonding, that is said to be the bond pair of electrons. Okay, valence shell contains valence shell electrons. Okay, so electron has the negative charge. If the two electrons present in the two pair of electron present in the valence shell, it will always repulse each other because it has same charge. Okay. So the depend upon that the order of repulsive interaction, okay, is lone pair interaction is repulsive interaction is very more when compared to the lone pair bond pair repulsion when compared to the bond pair repulsion. Okay, so lone pair repulsion interaction is very more when compared to lone pair and bond pair repulsion. I am taking the example as CH4. That is methane molecule, okay, CH4. So what is the valency of hydrogen here and what is the valency of carbon here? Carbon has the atomic number of 6. So it has the electronic configuration as 1s2, 2s2, 2p2. The outermost electronic configuration is 2s2, 2p2. So 2 plus 2 is nothing but of the valency of carbon. That is the valency of carbon is 4 here, okay. So hydrogen has the atomic number of 1. So 1s1. So it has the valency of 1. Hydrogen has the valency of 1. Similarly, nitrogen has the valency of 5. Oxygen has the valency of 6. Okay. So I am giving you the example methane CH4. Right. So here hydrogen has the valency of 1. Okay. So it donates its 1 electron to this bond. Actually this bond consists of 2 electrons. Right. So hydrogen donates its 1 electron and carbon donates its electron to this bond, right? So similarly, this hydrogen donates 1 electron, this hydrogen. Carbon donates its 4 electrons, like it donates its 1 electron to this bond, another electron to this bond, another electron to this bond, another electron to this bond. Okay, so here all are bond pair. There is no lone pair here, right? So it has the interaction of bond pair repulsion. It has the interaction of bond pair. So what is the angle, bond angle of HCH is? HCH bond angle is 109 degree 28 minute and it has the hybridization of sp3 and it has the shape of tetrahedral. Right? So next one is, I am taking the example as ammonia. Okay, NH3. So as we all know that hydrogen has the valency of 1. So it donates its 1 electron to this bond. It donates its electron. Nitrogen has the valency of 5. Okay. It donates its 3 electrons to make the bond pair, and remaining 2 electrons are present on the nitrogen atom and it acts as the lone pair. So here what type of interaction? Lone pair and bond pair interactions are there. Okay, lone pair, bond pair interactions are there. And here it is also sp3 hybridization. Okay, the bond angle between H and H, the bond angle between H and H is 107 degree. Okay, so structure is due to that sp3 hybridization, it has the structure of trigonal planar. Right? So the another one example is water molecule. Here hydrogen has the valency of 1, so it donates its 1 electron to this bond, it donates its 1 electron to this bond, valency of 6. Okay, so it donates its electron to this bond and to this bond, remaining 4 electrons are present on the oxygen molecule, so it acts as the lone pair here. So here also lone pair bond pair interaction occurs. Right, the distance, the bond angle of HOH is 104 degree. Okay, what it is? 104 degree. Okay, it has bench shape. It has bench shape or V shape. So therefore, what it concluded, the lone pair decreases the bond angle, right? So here there is no lone pair. Okay, so the bond angle is 109 degree 28 minute. Here there is one lone pair. The bond angle gets decreases from this 109 to 107. Okay, for this there are two lone pairs, no? So here from 107 to 104. So therefore, what it concluded, as the lone pair increases, the bond angle gets decreases. Okay, so another one case, that if the lone pair are present trans to each other, if it is present opposite to each other, then there is no change in the bond angle. Okay, I will give you the example for that. So in this case, the lone pairs are present opposite to each other. Okay, here the bond angle between FXEF is 90 degree. Okay, here lone pair and bond pair are present. So in this case, only bond pair is there, right? So here also there is no change in the bond angle. Here also FSF is 90 degree. It is because the lone pair are present opposite to each other, so that the repulsion is very less here, right? Okay. The next topic is Bain's rule. So now we are going to see about Bain's rule. Okay. So what is Bain's rule? So here more electronegativity element should be placed in the where percentage of S character is less in the hybrid orbital. Okay, so more electronegativity element should be placed in the hybrid orbital where the percentage of S character is less. That is what the concept here. And also more electronegative element prefer to stay at the axial position rather than equatorial position in a molecule. Why? That is only we are going to see here, right? So I am giving you the example as so the example is PCl3F2. Okay. So in this molecule, fluorine is more electronegative element when compared to chlorine atom. Okay. So now we are going to put the hybridization for this, that is sp3d. Okay. This is the hybridization of PCl3F2. And sp3d I can split up like this, sp2 and pd. Okay, what is the structure of this PCl3F2 is trigonal bipyramidal. Trigonal bipyramidal. Right. Okay. So how the structure will be? The structure will be like this. Right. So here in this structure, this is the structure of trigonal bipyramidal. Okay. So these two are axial position. These two are axial position. These three are equatorial position. Okay. In axial position, generally the bond are very weaker when compared to the equatorial position. I can write it like this. sp2, 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 and here pd, pd. We have already seen that more electronegative element will always prefer to stay at axial position. So in this compound PCl3F2, fluorine acts as the more electronegative element. So actually it prefers to stay at this axial position when compared to the equatorial position. Right? Okay. So now I am going to give you two structure. You are going to tell me which one is right. Okay. Yes. So this is the structure A and this is the structure B. So among these two structures, which one is correct? Actually, this is the correct. It is because in this PCl3F2, as I have already told you, that fluorine atom is more electronegative one. It always prefer to stay at axial position. Okay. So already the axial bonds are weaker. So if more electronegative element which are placed in the axial position, this compound, this molecule becomes stable. This molecule become stable. Already this bond is weaker, axial position is weaker. Okay, if less electronegative element chlorine will be placing on this position, means what actually happen? This molecules will become unstable. This molecule will become unstable one. Okay. So from the Benz rule to the conclusion, the hybrid orbital with more percentage of S character are more stable. Okay. So in trigonal bipyramidal geometry, we have seen an example PCl3F2 that has trigonal bipyramidal geometry. In this geometry, equatorial portion has high percentage of S character. Okay. Axial portion has low percentage of S character. Right. So and in equatorial portion, it is occupied by the lone pairs or multiple bonds. Right. In axial portion, it will be occupied by more electronegative element. Okay. Thank you.